Hello, good afternoon, everyone, and welcome to the second Numerics Efficiency and Software session. I have a bad news for you. Our second speaker, Mr. Joel Guerrero, can't make it, which is good news that the three other speakers have a bit more time to speak. Please, as I said already in the live Q&A on the right-hand side, questions will be answered at the end of every talk. Please ask them in the question box so that I can read them to the speakers. Yeah, so with that, I want to introduce Ms. Shannon Leakey from Newcastle University. She's going to speak about developing a Godunov scheme for the variable density artificial compressibility equations. Yes, please.
Let me just share my screen. Just assuming that you can see that okay. Yeah, okay. So my name is Shannon Leakey, and I'm in the third year of my PhD at Newcastle University. And today I'm going to be talking about a free surface solver that I've been programming in OpenFOAM. It uses the method of artificial compressibility instead of pimple, so it's a bit of a different approach. And artificial compressibility means that you can use methods for hyperbolic equations like Godunov type schemes. And then the free surface, it gets automatically captured by the contact rate in a Riemann solver. And also it's a lot easier to parallelize. So that's the real bonus about using this kind of method. So let me just move on to the next slide. Okay. This is not the same as artificial compression. I'm just putting that out there at the start in case it's like confusing, because it's very similar words. Although once you see the results at the end, you might think that I need some of that artificial compression that's in interFOAM. So these are the equations, the governing equations. In gray, we have the equations for variable density incompressible flow. And as we know, they involve pressure, right? But there's no equation for pressure. And so the idea of artificial compressibility is that you add a pseudo time derivative for pressure and also some other variables, but you don't have to do that, but I've done that. And then you advance in pseudo time, which is tau, until it stops changing. And when it stops changing, then you know that these pseudo time derivatives are all zero, which means you get back your original equations, which are the ones in gray. So that means that there's like two nested loops. It's called dual time stepping. You have one loop to go through the real time, which is t, and then nested inside that you have a loop for pseudo time, which is tau. And pseudo time has to converge each real time step to the incompressible limit. And just as an FYI, before we go any further, so here we've got viscosity, but I haven't actually implemented viscosity yet. Or I did, but then I kind of got rid of it because it wasn't, I thought it was a problem, but it wasn't. So that just does not appear again in this presentation, but obviously I will eventually need to put it back in. So as I said, it is a Godunov type scheme. So the variables like density, which you can see here, they're stored at the cell centers, right? And these get extrapolated to the cell faces, which is called muscle reconstruction. I'm not gonna lie, I don't actually know what muscle stands for. I think it's like monotone, upwind, something, 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 I don't know. And then this gets plugged into a Riemann solver to find the flux at each cell interface. So we have the left and the right states at each cell face. Plug it into Riemann solver, find flux, great. Okay, but you need to be careful because if you just use your standard gradients or whatever, you could end up with a situation where the density goes below zero, which is not good. So it's best to avoid that. And to avoid that, you use slope limiting using like TVD gradients, like superbeam, min-mod, that kind of stuff. Yeah, and that's to avoid getting Gibbs type oscillations and even like stuff that's unphysical. And I'll show you in a minute that kind of how this works. But basically, I was having problems just using this standard method to calculate the gradient for the pressure for the muscle reconstruction. So I kind of came up with another way of doing it, which was rearranging the momentum equation just to get this, right? That's at the incompressible limit. And then, well, the real-time source term, the real-time term is actually treated as a source term. So I already have this term. This term, you can just expand it using the product and chain rules to get a bunch of gradients of density and velocity. And then I just substitute in the TVD gradients for density and velocity. And then this is a gravity source term. So we already have all these terms, and I use them to calculate the pressure gradient for the muscle reconstruction instead. And that did a better job, which I'll show you in a second. First of all, just to say, I did start programming this in OpenFOAM, but it was quite hard to tell what was going on, apart from that it was going badly. So I took a detour and I wrote it all in Python for 2D Cartesian meshes, sort out some problems. At the end, I'm going to bring it back to OpenFOAM, but we're going to go on this detour and I'm going to show you a few results. I've written it up as a paper that we're just editing at the moment before submitting it to a journal. So here are some of the results. First of all, I did some Riemann problems in pseudo time, 1D Riemann problems, to test different Riemann solvers to calculate the flux. And they're all pretty similar apart from the row Riemann solver, which has a bit of an issue at this kind of case. And also I can count, I know it says 1, 2, 5, there were other ones. They were quite boring and it's quite a small slide. So, okay. And the next test I did was the first real time step of a dam break. So that's after pseudo time convergence. And what we're looking at here on the right are the cross sections across the bottom row of cells. And each of these rows, that's a different slope calculation for the muscle reconstruction of pressure, which is demonstrated here. Literally everything else in the simulation is the same, like all the settings. The only thing that's different is how it calculates the slope for the pressure reconstruction. Min mod and super V, they're just like standard TVD gradients. And you can see at the density discontinuity, well, there should be a pressure gradient discontinuity. That's the kinematic boundary condition or the dynamic boundary condition. But there isn't if you don't do anything special, because it's taking information from both sides. That's why that's kind of off. And then that results in an imbalance of forces, and then the density goes above 1,000, which it shouldn't do because it's incompressible. So whenever I use my new method, which is this bottom row, when I rearrange the momentum equation to get the pressure gradient, it actually works like quite well. I was surprised because that calculation of the pressure gradient does not include the actual value of the pressure in the surrounding cells. So I was so surprised that it worked so well. And then it kind of, yeah, the error in the density is a lot less. So that is nice. And then there's a few more steps of a dam break. It's quite a large domain that I'm not showing all of it. There's about half of it because it has to get all the way to the end to compare against experimental data from 70 years ago. Obviously, that's not my experimental data. And it compares quite well. So the experimental data is the black crosses. This column is like a small dam break, and the right column, the big dam break. It's all been non-dimensionalized, so you can compare everything. And it compares quite well. To be honest, the Riemann solver and the pressure gradient calculation don't really change a lot, if I'm honest. So I solved my problems in Python, and I've put the solver back into OpenFOAM, which is still a work in progress. And it should work for arbitrary unstructured meshes in parallel. I'm just like testing a few things to try and improve it. So it's kind of inspired by Foam Extends DBNS Foam, but I wrote it from scratch, and it generally ignores the numerics in OpenFOAM, apart from one thing, which is the muscle reconstruction. For the standard muscle reconstruction for density and velocity, I just use FBC grad. But for the pressure gradient, I use this special thing I was talking about earlier. But it's important to note, you can't just use any grad scheme because you want to make sure it's limited to avoid those Gibbs type oscillations and it blowing up. So for that, I used cell limited cubic or Venkatakrishnan. I'm not sure if that's how you pronounce it. I've never heard anyone say this guy's name, sorry. And yeah, so then that means you can reconstruct it to the faces. But the problem is when it's an unstructured mesh, you don't know which orientation it's kind of facing and what that is with respect to the velocity directions. So you need to rotate it using a 3D rotation matrix. So each face you need to rotate. So I did this using surface tensor fields so that each face you could have a rotation matrix, and also actually an inverse rotation matrix. And then so you rotate it, you solve the Riemann problem, you rotate it back. And to solve the Riemann problem, we use a Riemann solver. I know I said at the start the row Riemann solver was the worst one, but it's the only one I've done in OpenFOAM so far. I just haven't got to the other ones yet. And yeah, it involves multiplication of 3 5x5 matrices, which I'm currently doing with the Armadillo C++ library. Maybe there's a better way. I think I'm going to have to do it, like multiply them out manually, because there's a lot of, not a lot, there's a handful of zeros, which is kind of unnecessarily multiplying out to get a 0 when I know it's going to be a 0. So I could probably make that sped up, but it's okay for the moment. And then, yeah, you just add up all the fluxes using XC surface integrate. So here is the solver applied to a dam break and compared with interfoam. I'm going to go through a few slides in a moment. There's no viscosity or turbulence or surface tension. Yeah, and I know that it's very diffusive. Like, yeah, I know that. But also, you know, it kind of hits things at the same time. So that's promising. Oh, and here it is in 3D. And you can't see the diffusion when you display it like this, but there is diffusion. Yeah. Okay, so problems. As I said before, diffusion. And I guess I could use like an artificial compression term, like an interfoam, to get rid of that. That's actually not my biggest problem at the moment. A slightly bigger problem that you couldn't see in those images because of the way I displayed it. But if you change the color bar, there was a tiny bit of the problem I thought I got rid of. The density going above 1,000, and I think it's to do with the complicated pressure field around this area. But I have an even bigger problem than that at the moment, and that is this convergence. So these are the residuals. They should go to 0. They don't always go to 0. This is residuals like in converging to an incompressible limit in pseudo time. So it needs to go to 0 every single real time step, and they don't. And well, I looked it up and I read about it, and this is a problem that you can get when you're using limiters on unstructured meshes for like muscle. And I looked at the source code for the gradient limiters to kind of work out really what was going on. And I found a bug. So the cubic polynomial in semi-limited cubic, which to be honest, I didn't actually even know this existed until I looked at the source term, not the source term, the source code, there we go. What it should be is it should be this purple line there, and it should smoothly go up to 1, so it's all differentiable. But actually in the source code is that pink line, and it goes up, and that's just completely not differentiable, so it can get stuck on either side of it and just never converge. But I've reported that as a bug in between making these slides and talking, and it's going to get fixed. So yeah, but I've fixed it myself in my own kind of code, and it actually does a bit better. But what really helps is if you switch off the limiter in areas of uniform flow, that really helps. So I need to, that's what I'm looking at the moment. I haven't got to the end of it. So yeah, that is the end of my presentation, and I'll be happy to take any questions. And there's my email address if you want it.
Okay. Thank you for your talk. I was just going to tell you that you have 3 more minutes. I just have to refresh the browser screen because I haven't seen any questions yet. Yeah, just 1 minute. So, but basically the redoing in Python that's not related to the stuff that Herv talked about in his keynote. That's a different project. I don't know if you.
That's a different thing. But now I know that exists. Like that would be nice to know that existed before.
Okay.
Yeah,
So, any questions? I don't see any in the Q&A bar. I think then we can assume that wait a minute. Yeah, there's a question from Saeed Salehi. if all the problems are solved, what will be the advantage of the artificial density compared to pimple loop?
Okay, I'm assuming he means artificial compressibility.
Yep.
Yeah, so the advantage is that it's quite easy to parallelize. People have like programmed these very easily on like GPUs and stuff, and with good scaling. So technically, if you were running it in serial, it would be more expensive computationally, but there's a real, yeah, if you were to parallelize it properly and you really knew what you're doing with parallelization, which is not me, then you could get a real speed up and you could take advantage of that, because it's all these local Riemann problems and it's all very localized. It's explicit in pseudo time.
Okay, thank you very much. That would have been good in the beginning as a motivation for the talk, but it's good the question came up. Okay, for everybody who has been switching to this session because he wanted to see the talk of Mr. Joel Guerrero, Mr. Joel Guerrero can't make it, and therefore the next talk will be by Dr. Ilya Popov. I think he's talking about something that is very important, because usually people think about how many cores a CPU has. And the interesting stuff for CFD computations is not the number of cores, but the memory bandwidth. That's usually the limiter in my experience. And I hope that question will be answered now for all times. Okay, thank you very much, and please start.
Hello, thank you for introduction. Yes, indeed, I will be talking about a technique or a number of techniques, how we can optimize CFD codes for memory locality, and especially given, let's say, limited computational resources, limited number of cores. So normally CFD codes use locality of fluid dynamics equations to divide a domain into multiple subdomains and compute them in parallel. And this is already used in OpenFOAM. We can reach scalability up to thousands of cores, but the same principle can also be applied on a smaller scale to take advantage of different levels of CPU architecture. This is, for example, used widely in matrix multiplication algorithms, where people divide matrices in blocks related to sizes of different levels of cache. And we can also use similar principles for CFD applications. So we can subdivide our domain into even smaller domains that correspond to the size of L2 cache, for example, such that all the data needed to compute this small domain can fit into L2 cache. And in this talk, we will demonstrate this approach on a modified OpenFOAM species transport solver, and we'll get about 3 times performance boost. And this is indeed especially important if you have limited CPU resources and want to get most of your limited resources. So this is our simplified demonstration case. We will solve a convection diffusion equation for a number of species, like 10 or 50. And to do that in OpenFOAM way, there will be a loop over species, and for every species we will call the usual solve function with the equation. And this means that OpenFOAM will make a number of passes over data to compute a gradient, then a limiter, then Laplacian, then convection term, and then update the field. And the problem here is that every pass over data pushes all the data out of cache. And we will see how we can change that and how we can improve performance of this CFD code. Modern memory hierarchy is multi-layer. And this is kind of different from what it was 20, 30 years ago when OpenFOAM was created. So nowadays, a server which we use for simulations use a number of cores. Each core has a dedicated L1 and L2 caches. Then a group of cores can share a next level cache, L3 cache. Then a group of cores can also have a RAM block, so they form a NUMA node, non-uniform memory access. And then a number of sockets will sit on the same in the same machine, then connected to other machines by MPI. So there are multiple levels of memory, and on each level, access to our own data is much faster than access to the neighbor data. And we can take it, well, basically to maximize the performance, we have to take into account this multi-layer architecture. So going back to our species transport solver, OpenFOAM makes a number of passes over data. And if the amount of data needed for each pass is larger than cache size, that means that each pass will push all the data out of cache, and then the next pass will have to read all this data again from RAM. And this and the total number of data we process we cannot change because it's determined by our problem size, by our mesh. But what we can do is, if we divide it in smaller domains, if the amount of data in one smaller domain fits into a cache, then the data that's read on the step 1 will stay in cache for all these steps, and we will have less memory loads and quite a nice performance gain. So there are several, let's say, steps, several techniques we can use to minimize memory loads. One of them is fuse loops. So instead of many loops over cells and faces, we can fuse them and do only 3 loops over cells and faces. Then next technique is dividing into microdomains. The size of microdomains shall be chosen such that all the data needed fits into L2 cache. And for the case of 10 species, that means that we will need about 500 bytes per cell, and to fit into typical L2 cache, the size of microdomain should be about 1,000, 2,000 cells. In this demo, we use decompose par utility with multi-level Scotch decomposition. So first level will be decomposing into MPI nodes, and then a second level will be decomposing into microdomains. So this is how that can look like. So white lines divide into MPI domains, and then color indicates these small microdomains. Each one is about 1,000 cells, and there are 400 microdomains per every MPI domain. And then instead of one loop over species and then a loop calling solve function that loops over all the domain, we would like to have a loop over microdomains. Then for each microdomain, we will, for each species, we will solve this equation in the microdomain. This is a pseudocode. This is not something you can type in your code and compile it, but this just provides an indication how we would like it to look like. Currently, OpenFOAM functions are not microdomain aware, of course, so we had to re-implement gradient, Laplacian, divergence, all these functions. Another important thing here is that this division into microdomains, it does not interfere with boundary conditions. So boundary conditions is a separate thing, and division into microdomains only makes sense when boundary conditions and MPI exchange takes a small fraction of time. But this is indeed the case because we, from the start, we consider it the case where the data per MPI domain is large and doesn't fit into the cache. That means that the number of boundary cells which will be small compared to number of internal cells. So this, not I'm concerned. Another interesting technique is swapping the loops. So performance actually depends quite a lot on the order of loops. So for example, here are two options. One is outer loop for species and then inner loop for microdomains, or outer loop for microdomains and inner loop for species. In the first case, we can notice that each species actually uses quite a lot of same data. Gradient coefficients, cell centers, phase areas, and these fields have to be loaded over and over for every species. So then changing from the structure on the left to structure on the right, we can reduce the number of loads. And here are the results of this demo case. So this was 8 million cells mesh divided into 20 MPI domains for 10 species and for different microdomain size. And performance here is relative to the OpenFOAM code. OpenFOAM code is in blue, and then depending on microdomain size, we have two options with different loop orders. And we can see that indeed microdomain size about 2000 cells is optimal, and we can reach about 3 times performance increase for this case, which is quite nice. And then, so how can a user of OpenFOAM take advantage of these techniques? Well, first, we have to create these microdomains. Currently, this we provide a utility to do that. Basically, what it does is first it calls decompose par with multi-level decomposition. Then it post-processes the result of the decompose par, and then it calls it again with only one layer of decomposition, but preserving the order of microdomains. Then the user has to modify the code of their solver. Well, current OpenFOAM finite volume functions are not microdomain aware, so we had to re-implement all these functions, gradient, limiter, flux, Laplacian. good news is that microdomains do not interfere with boundary conditions. So the boundary condition exchange is just normal OpenFOAM exchange and is done separately from microdomains. And you can, we have published the code of this very simplified demo case, so you can look at how these techniques can be implemented and maybe use some of these techniques in your own code. Yeah, so basically that's it. And I thank you for your attention, and I would like to answer any questions if there are any.
Yes, thank you very much for this very interesting talk. I think there was one question that I see in the chat by Patrick Höhn that is half answered. I think interesting topic, in which OpenFOAM flavor are microdomains available. So they are not yet available, as I understand it, but with which flavors do you currently develop it?
Well, for this demo, I was using OpenFOAM 2012, and indeed, none of this is available in OpenFOAM. And yeah, so basically, we had to re-implement a number of OpenFOAM functions to be microdomain aware, but well.
Yep.
In the future, we can think about how this can be implemented, how this can be integrated into upstream OpenFOAM. Yeah.
Mm-hmm. Then there's a question by Leonardo Miranda. Interesting. Could this lead to convergence problems?
In this formulation, no, because the only thing that's changed here is the order in which cells are processed. So this does not change the computation itself, only the order in which the computation is done. Mm-hmm. There is a thing where this may come up, the question is, for example, if you want to make a next step and integrate it with, for example, OpenMP, then if you process these microdomains in separate threads, then you have to think of how you synchronize between this, and if not done carefully, this can affect convergence.
Okay, then there are three more questions. One question by one Mr. Henrik Rusche. Most solvers spend substantial time in the linear solvers. How could this work with microdomains, especially preconditioners?
Yes, so I got a backup slide for this. Indeed, so what I demonstrated in the presentation was explicit solver, and this is not something that's the most kind of used. For implicit methods, well, implicit methods, they solve a matrix equation, something AX equal B, and they do it with iterative solvers. And iterative solvers, they are based on a number of primitives, mostly matrix vector multiplication and some vector operations. And all this can be done also in microdomains order, especially matrix vector multiplication. There are a few things that need special attention. These are dot product and norms, which need data from all microdomains together. So this, how this can be organized is that for every iteration of the solver, we can do it for microdomains, but then when computing norms or dot products, we have to actually synchronize and bring together data from all the microdomains.
Okay, thank you. I think we will cancel the other questions. And if you want to discuss with Dr. Popov more about it, please reach out through the forum software to him. Okay.
Yes, thanks.
Thank you very much. The next and last speaker for this session is Dr. Andrew Snappy Jackson. He will talk about improvements to low Y+ mesh generations in Helix, which I think is something that he knows some things about, and I'm looking forward to it. Thank you.
Hopefully. Yeah, thank you, Bernard. Yeah, my title of my talk is looking at some stuff we've done on low Y+ meshing in Helix over the last, well, particularly low Y+ has been focused for the last year's work. So the agenda of the talk is just looking at mesh generation we do here at NGIS, a motivation for the current work, some methods we've developed to support full layer coverage, and some enhancements that we've made to this method for looking at low Y+ meshes, some conclusions. So we've worked on Snappy Hex Mesh for quite a number of years. We introduced Snappy Hex Mesh at the 3rd OpenFOAM Workshop. So that was almost 13 years ago. I was work with my colleague at NGIS, Eugene de Villiers, myself, Matthias Janssen at OpenCFD. Since then, we've worked on a version of Snappy Hex Mesh that we call Helix Hex Mesh that we continue to develop here. So the current work that we're looking at is we were interested in generating low Y+ meshes. So this is typically we want to generate meshes of up to around sort of 20 surface layers. And so we're talking about very high aspect ratio cells at the surface that we need to generate. And underpinning this, we've got to use a robust methodology so we can generate these meshes error-free and also have in a timely fashion. So I'm going to quickly, Helix Hex Mesh in what we call sort of classic mode is very similar to Snappy Hex Mesh. So we have all the features that probably people who use Snappy Hex Mesh are used to. So surface, feature, and proximity-based refinement. And then inside, outside, and distance-based volumetric refinement, and all the features for sort of capturing cell zones and face zones, and then the snapping and feature capturing stages are available, and also if you want to add layers, layer projection method is available. So these the classic approach is it's very robust framework for mesh generation, because basically at every stage of the process there's a reversal mechanism. So we started with a castellated perfect mesh with so we can always revert back to that previous state, valid state, which will guarantee the final quality that we set in our dictionary control is obviously fully parallel. But it does some of these problems of the reversal, or obviously can lead to sort of local layer collapsing where it cannot satisfy quality. So on anything but sort of very simple geometries, it's just not possible to get 100% layer coverage. And by the nature of the reversal mechanism, things like adding layers is very much iterative in nature. So you add layers, find the errors, revert them, and continue until you've created an error-free mesh. And this is really the only method that is used for sort of guaranteeing the quality of the mesh. There's no smart optimization tools available that we use to improve the local cell quality. It's what you've set in your control dict. So the first incarnation of a full layer coverage mesh was what we call the dual mesh, which we introduced at the workshop a few years ago. It's we try and use as much as available in the snappy hex mesh so we start with basically a refined castellated mesh, and then we have to split at the cells at refinement interfaces and also at the boundary before we then calculate the dual mesh, which by the split when the dual is created, it creates a layer mesh on the surface. So this is then snapped to the surface, and then the single layer we can subdivide into as many layers as we want. This is also add a lot of optimization to make sure that the quality at the end is good enough to run. So this dualized approach, it does a good job at sort of reducing the jumps in cell volumes at refinement interfaces, and obviously it's a method for generating 100% layer coverage. And also, obviously, this method has a lot of smarter optimization methods to improve the overall mesh quality. But one of the reasons we sort of wanted a different approach is because we use the adaptive mesh refinement AMR technique for after the meshing to when we're solving. So the problem with this dual approach is because we're not maintaining hex cells at refinement interfaces, that it really does make it very limiting for adaptive mesh refinement. And also because you're splitting the cells at these refinement interfaces, you're also getting larger cell counts as well. So in the last couple of years, we've worked on a new method. It's called Extrude, but we want to use as much of the features we've learned from the classic and the dual mesh. So, but we want a method that will only generate hex and split hex cells. So all cells in theory, even layer cells, but we don't really want to do that. Could be refined by using the AMR approach. And again, but this is like an improvement on Snappy that we want to, the full layer coverage by using this method. We use all the smart optimization that we've built from the Extrude measure, and also there's some issues with Snappy capturing thin gaps because it sort of has to throw away cells because it might cause snapping issues. But this can sort of preserve some a bit more information of the in gap regions, so you can sort of it does a bit better job sort of resolving them. So in the Extrude method, we would use all the feature surface proximity and volumetric refinements to get a base castellated mesh. And then after this, for every boundary face, we extrude a zero-sized cell to ensure that it sits the right size of the geometry. And then we use, to inflate this method, we use a cell, it's called cell sphericity optimization, essentially to make the cells as spherical as possible, as close to unit aspect ratio, where there is space for that to be done. And then we just reuse as much of the snapping as we've got from the classic approach to capture all the features as well as possible. And then as the final step, we just can subdivide that single layer into as many layers as we want. So I'll just talk a bit more about what sort of layer projection method that we use to inflate the layers. So it's primarily driven by we're trying to match the outer layer cell by using a volume weighting from the inner to the outer layer stack. And then for the layers themselves, we want to keep the surface, use the surface normal direction, and we blend from surface normal direction to the outer layer stack point. We also have some constraints on, so we allow face zones to be grown up, and these could include sort of non-planar zones if you want to. So there is constraint on the direction of the normals. And also we have some constraints on normal direct growth direction for sort of sharp training edges and baffles to avoid negative pyramid volumes forming, which I'll discuss a bit later for the low Y plus meshing. Again, there's during the optimization, during the layer projection, we're always optimizing, particularly to get rid of critical errors like pyramid volume errors, which can be quite harmful when trying to solve. And we try to, as much as possible, to minimize mesh orthogonality errors, although we do allow face orthogonality to go above 70 degrees. It's very difficult for when you're having a high number of layers to enforce a low orthogonality for these type of unstructured meshes. We also do have, before layers are added and after layers are added, we do have mechanisms, so we can handle sort of collapsing of layers, or just so where the optimizers just simply cannot, maybe it hasn't resolved the region very well and it's really become scrambled. We have sort of methods to try and to remove any final errors that may exist in the mesh. So we've got the basic method. Now we're sort of trying to, it works quite well for higher Y plus values, but really when adding more layers and getting the first cell height smaller and smaller, it's the majority of the errors are when you look at trying to add layers in highly concave and highly convex corners. So if you think about issues squeezing a high number of layers into acute angles like tire contact patches, or if you're looking at a sharp trailing edge, and for example, a sharp trailing edge for an aerofoil spanning, and having layers wrap around that edge can be quite a tricky problem to achieve. Another problem is that it's in general, it's because we always starting with a background Cartesian mesh, and this is on anything but complex geometry. It's you cannot align this mesh with the geometry itself. So when these elements snap to the surface, the quad faces can have a high level of face warpage, which is greater than the actual the first cell height that you specified. So when the faces are not aligned and the face warpage is of the order or greater than the first cell height, then we split the hex elements into prisms to avoid the formation of invalid elements. Another enhancement we've been looking at is to, as I mentioned, sharp trailing edges and baffles. It's very easy to introduce errors when wrapping the layers around these sharp edges, particularly the face that spans the top and the bottom lower surfaces. So I mentioned that for the projection, we're careful in the direction that the normals can grow for these edges. So, but it's basically really not very good for the face that's connecting the upper and lower surface. Can be a source of numerical error. So to try and improve this, we've used as it's like a extruded fan mesh, which tries to extrude from the layers, or the stack layers that connecting the upper and lower surfaces, to help with the transition around that edge. So it doesn't really help with the removing sort of likelihood of pyramid volume errors, but because we have to terminate these extrusions, you can get high orthogonality at these terminations. So it's sort of ongoing work. So really, the sort of take-home message is we're trying to develop new methods for generating sort of full layer coverage without the need for local layer collapsing. People are always complaining about this, so we're really trying actively to improve it. And the current focus is in it. Then people want layers, but now they want very low first cell height. So the current focus is developing layer meshes for modeling low Y plus scenarios. So we are trying to push as many layers up to order sort of 20, improving the mesh, looking at improving the mesh topologies in critical regions, and also minimizing orthogonal faces in the mesh. and always at the background, we're looking at sort of improving the performance and the high core count scaling of these meshing techniques. So if you have any questions, I'll be happy to answer.
Okay, thank you very much for this talk. I'm just waiting for questions. I don't yet see any. About the missing presenter, I just reached out to Mr. Joel Guerrero, and he told me he will not be able to give his presentation during the workshop because he lost his access to his data and his backups, which is, yeah, I think, yeah, thoughts and prayers. Yes. Yeah, there is a question by Dragana Dimitrijevic. Thank you very much for the nice presentation. Is it open source or not? I missed that information.
Unfortunately, it's well, we're sort of a very commercial focused company, so it's generally our customers. Well, it's all open source, but it's only really we provide it to our customers. So that's sort of standard snappy hex mesh for. That is our open source variant.
Mm-hmm. Okay. Yeah, there is one more question by Rui Cesar Silva. Can we choose the target Y+ at the moment?
You can, yes, you can specify a Y+, and it will match that Y+. The only reason it won't match it is if the optimizer has the capability to move points off the surface, but they tend to be in non-critical areas where it does have issues. But yeah, it should satisfy the target.
There is just one more popped up. Is there any limit for the total number of mesh? I guess it's mesh cells. Is it also possible to create around 200 million for fighters? Also include 20 billions?
Yeah, if you go to sort of 64-bit labels, and then there should be obviously. Well, I can't talk about it, but we are actually working on something that is sort of the next generation mesh, which we'll hopefully present maybe in the next workshop, which is looking at much bigger, this 20 billion or more cells.
Mm-hmm.
But you can still do it with this, but it's yeah, you'd have to run it on a lot of cores.
Mm-hmm. He just clarified with BL he meant 20 billion. Sorry, not boundary layers. Okay, again. Okay, so, but I think, yeah, I think that's it with the questions.
Yeah, I was to say the 20. That's the sort of target. So we're not. We can get reasonably good, from 12. But when you sort of push beyond 12, it gets a lot. And especially if you really drop the first cell height, it becomes a lot sort of more challenging. So this is why we're having to do these other methods to make it possible.
Okay, so thanks everyone. And if you have more questions to Andrew, I think you can get him through the Engis.
Yeah, sure. Yeah, no worries.
Session. And yeah. Thank you very much. I think this concludes the session. I wish everyone a good whiskey experience afterwards. And yeah, see you.
Thank you, Bernard. Right, cheers. Bye.